Hi, I'm Meta Spencer. And today, I guess we have to go some traveling and pleasant places and not so pleasant places. Because life has been hard the last little while in Jamaica. There's been Melissa, and isn't that her name, Melissa? The hurricane? Yeah,
Yes.
okay. And my friend Tom Goreau is from Jamaica, and I want to start off by giving a nod to him so that he can tell us how things are going or how things went very recently, the last few days in Jamaica. Tom is a marine biologist, and he's the president of the Global Coral Reef Alliance, and we've talked several times on this show before. And when we get through with Jamaica, we'll go to the Arctic, and I want to introduce you to Ulyana Horodyskyj, who has just returned from an expedition from across the North Pole, all the way around the Arctic. And she is the head of the communications center on the Climate Change Center at the University of Colorado in Boulder. So we're going to have an interesting expedition today, going from Jamaica all the way to the North Pole and around. So, Tom, what's the story? What's about your home country?
Well, it's too soon to know. Jamaica was hit 2 days ago by the strongest hurricane ever to hit land. And, they're exponentially worse the stronger they get because of the force of the winds and so forth. But, when they're very strong, they're spinning so quickly that the eye of the hurricane, which is where the worst damage is, actually very small.
Oh,
And so, really, I mean, when it's spinning slowly, the eye widens. When it's spinning very fast, it kind of contracts. And so,
oh,
it's just a kind of a trail of catastrophic damage, which basically all the buildings seem to have lost their roofs or been flattened. Well, the last hurricane, let's just put it this way. A hurricane took the roof off our house when I was 1 year old, and that was at that time the strongest hurricane ever to hit Jamaica. But now, of course, it's small compared to what has happened since, because we've had about half a dozen hurricanes since then that have been pretty much sort of steadily worse, and that's driven by global warming. That's simply more heat in the surface ocean, and that's something we measure accurately from satellites. And what's happened in this particular hurricane is that there was a high pressure ridge that pushed it, held it in place. And it just kind of sat there for about a week or two, just south of Jamaica, getting stronger and stronger, but not moving because it couldn't, because it was the high pressure in front of it. And then all of a sudden, about 2 days ago, a gap opened in the kind of the pressure distribution. It was kind of a narrow, low pressure gap, and this thing just shot through it suddenly at high speed after having, sat still for a couple of weeks. But anyway, it had built up tremendous intensity. It went over the most mountainous parts of both Jamaica and Cuba, and those mountains broke up a lot of the force. But in fact, it's devastating the Bahamas now with about 25, 30-foot waves, and those are going to hit Bermuda in the next day or so. Yeah,
yeah,
it's
yeah.
catastrophic. And, from my point of view, it's a direct sign of global warming. This is
Sure.
why these things
Yeah.
get stronger and stronger, and why the next one will be worse. And in the meantime, we've lost all our natural coastal defenses. Our reefs, our corals have died from global warming. We've dug up our mangroves and seagrasses. And so there's nothing left to protect the next time, because all our natural protection has been shredded by this event. So with global warming, every place is getting hotter, and the tropics are paying the price of just a tenth of a degree or so of warming is causing these storms to be more ferocious when they hit. Um, but at the same time, oddly enough, warming is greatest in the poles. So the gradient of heat between the tropics and the poles is actually decreasing. And so that affects global atmospheric circulation, affects global ocean circulation in ways that have profound feedbacks to future global climate change, and they aren't really in the models.
Okay, Uliana, so you've just returned from a big expedition. And you came home sick, but you're well enough to talk to me a little bit today. I'm glad to know. So tell me about this expedition, what you were looking for, and what you found.
Sure. And then just to bring back what Tom was saying, it all is connected, right? So you have this temperature gradient that used to be a lot more extreme between the tropics and the polar regions. And
Mm.
now that it's less extreme, meaning there's not as much of a difference because the Arctic's warming so much, that affects the jet stream, which means that affects global weather. And I think that's such an important point that this is a whole system that we're looking at. And we're looking at it through different lenses and different parts, but we're finding that it is connected. So I love hearing from Tom's perspective in the tropics and knowing that, yeah, it is actually connected to what we're seeing up there. So this ship was a polar class 2 vessel. It's a tourist scientist hybrid ship, meaning that passengers were going to go see the North Pole, but at the same time there are scientists working on board. And it uses liquefied natural gas, which lessens the impact, to an extent as far as the emissions. There's not much of the black carbon coming out, which is a lot of what I'm studying. And then the idea is to not really be breaking through ice and making the problem worse, but finding any open water stretches and open leads, the parts where ice is drifted apart, to get the ship through. So it's a way to be doing research and seeing these places while trying to have them a minimal impact, while doing it.
Just a
And
sec. And did you say you are you somehow you're doing pushing ice aside? Did you have to break ice or anything to get through?
in some parts, we did have to break ice, but one interesting observation for me was how silent it was in some nights. I'm like, we're like at 86 degrees north, for example, heading towards 90, and it's pretty quiet. I was really expecting it to be really loud and breaking ice. I've been on an
Oh,
icebreaker, down in Antarctica a long time ago now, back in 2007.
yeah.
And I just remember the screeching, groaning, hitting, and it was, so that for me was a really interesting thing. I expected it to be a lot noisier. And so when I looked, my balcony, you could see, well, there's a lot of open water. And this is at already 86 degrees north. We're approaching the North Pole. We're not that many nautical miles from it at that point. And the ice that we were going through when we were hitting ice was really thin. And so it's this what's called the first year ice. So it's the ice that forms from that first winter. The problem in the Arctic is we've lost a lot of the thicker multi-year ice. And that is what causes the Arctic Ocean to be more resilient to warming, right? Because we have this thick ice, it's not so easy to melt. It reflects back the solar radiation and it keeps the ocean cool. A lot of that now is near Canada, and there's just in the last 40 years we've lost most of that. So that for me was stunning to be like, we're approaching the North Pole, and the ice is really thin,
Uh,
and it's not as resilient. And so I was able to get out onto the ice then, and take a look at some of the snow covering the sea ice. And it looks visibly quite clean, right? But then when we collected some samples and filtered it down, could actually see microplastics like these. For example, just one sample from the North Pole had these orange and blue threads, and then a big chunk of black carbon right in the middle of it too. So that's something I hadn't seen before. Both pollutants, the black carbon, which comes from industry, it can come from factories, from ships, from cars. The long range transport is typically from North America that time of year, but it could also be coming from Europe. And so the microplastics, though, I was recently reading a paper saying a lot of that stuff can actually come a long way as well. There's a lot of long range transport possible now, to the point where they're finding it on Mount Everest. So
Finding what?
microplastics and nanoplastics on Mount Everest that are not just local. Right? You would expect local pollution from climbers and bringing ropes and things, but
Mount
they're actually,
Everest. Mount Everest, the find.
yeah.
Yeah. Oh.
So from the tops of the highest peaks of our planet
Uh-huh.
to the polar regions, which you expect to be these remote, pristine places, we're finding it.
Yeah.
Now, the North Pole wasn't the last, it wasn't the end goal. We were actually going all the way to Alaska. So
You're
then
starting where again?
we started in Svalbard, Norway. Yeah,
Yeah.
so it's an archipelago that's about 1,000 kilometers from the North Pole. So we
Mhm.
started from there, and it was surprising like how quickly we got up to the North Pole, because again, it was not difficult conditions, just because there's a lot of open water.
Mhm.
And then after that, we went to the magnetic North Pole and then something called the Arctic Pole of Inaccessibility. So the magnetic North Pole is on the move, right? So it's the one, right? We have a compass, and where does the compass point towards? Not geographic North Pole, but the magnetic North Pole.
Mhm.
Why do we have a magnetic North Pole? It's because of the core of the planet has this molten part. It's constantly in motion, and that generates these electromagnetic currents. And so that's how our compasses will detect that, right? And so we were literally chasing the magnetic North Pole because it's on the move based on what's happening way deep down the Earth's core. So that's fascinating to me.
When they say the North Pole, magnetic North Pole is moving, I thought it might, be talking like an inch every 500 years or something.
20 years ago, it was in Canada, like the Canadian Arctic, and now it's in the moving towards Siberia. So it's closer to Siberia now than it is to Canada. 55 kilometers per year right now. That is massive. I was really surprised to learn that. And something's going on just with a lot of activity, in the core. And so that's an active area of research now about tracking how fast it's moving, what's going on. Does that mean our pole is going to reverse? Because we have a history of that happening geologically. That is happening.
What would happen if I've heard that could happen? What would the effect be? Would we feel it?
There's no doubt the Earth has gone through hundreds of magnetic reversals in the geological past. They're accurately dated, very accurately dated, so we know when they happened. The last one was, I think, about 700,000 years
Yeah.
ago.
Mhm.
And but the thing is, I mean, the whole pole flips now. The fear that some people have is that because the Earth has a magnetic shield protecting it from radiation from the sun, that you might get a huge influx of solar radiation, ultraviolet, charged particles, all sorts of things that might reach the Earth that are protected, that were protected from the magnetic field. And some people speculated that that could cause extinctions on a large scale. Now, in fact, people don't see any clear correlation as far as I know. I haven't looked at it very closely, but I mean, I did know a whole bunch of geophysicists who were just into measuring magnetic orientations and
Mhm.
sediments who worked with paleontologists who are identifying the same fossils that were in the same sediments. And they couldn't find any clear correlation at that point. And I think that's true. So, I mean, it may just be that the transition is somehow gradual, or that
Mhm.
there are other things that protect us from it, or the fact is it's easy to speculate about doomsday scenarios, and that when reality is often a little more complex than we imagine. I think
Yeah.
that happened here.
That's what that corroborates with what I know, and I'm not a geophysicist either, but from what I've gathered, from what I've read, is that it's not an instant reversal, that it takes many, many years actually for that reversal to happen. And of course, it's going to affect navigation for a bit. Systems will have to change the way animals migrate. They'll follow magnetic fields, and so that'll change. But
Mhm.
I also have not read anything really that says there will be anything massively disruptive.
But they would have to be changed. I mean, for instance, there are magnetic bacteria that orient themselves
Mhm.
to poles, and they behave differently in the north than the south. They go in the opposite direction. So they would have to relearn to orient themselves
Right.
under those
Mhm.
circumstances.
But they'll probably have the time to it because, like I said, I think from what I've read, it's not instant. Like, oh, okay, now
Yeah,
the South Pole's north.
yeah,
Every
yeah. Well, I would say that if there were a very dramatic biological effect that the paleontological record would show some
exactly.
transition, it doesn't seem to be there. Now, I mean,
Mhm.
let me, in terms of that, I mean, let me bring up something that's closer to what Ulyana does work on, which is to say methane bombs.
Mhm.
Okay,
That's
and
much more serious and timely.
well,
Yes.
potentially. I mean, so there's a lot of concern about the possibility that a lot of frozen methane is trapped in permafrost
Mhm.
and in the Arctic come out suddenly. Now, I do want to mention, first of all, what Atlanta's doing is not new. This is cover of Nature from 2011,
Wow.
vanishing Arctic ice, and it's got 2011. Okay,
Hmm.
it's got a whole set of issues about how the ice is disappearing and all of that. And the fact, I'm sorry Peter Wadhams isn't on
Mm.
because he's pretty much the person who's responsible for discovering most of that. But anyhow, and all these issues have been around for a long time, and we just ignore them and don't take them
Hmm.
seriously until they get totally out of control. And the point is that when the Arctic ice disappears, which is on the verge of doing. We've had, now, you see, let me explain. I got into this because I developed the method for predicting bleaching from satellite data. So I track sea surface temperatures worldwide, and I developed the index for extreme temperature events. And I was look for coral bleaching with that. But in fact, the most severe events that we're seeing now are in the Arctic. The temperatures have
Hmm.
gone up in some cases 10, 15 degrees C above average.
I'm sorry,
Uh,
as opposed to the Antarctic or as opposed to other parts of the
well,
world.
in the Arctic mainly, because remember, the Antarctic is a huge pile of ice on a high continent for the most part, whereas
Hmm.
the Arctic is water. And when the Arctic melts, it's all open water. And in fact, we're on the verge of that right now. And that changes the reflectivity
Mm.
amazingly, even if we weren't dumping aerosols and black carbon and all sorts
Right.
of garbage on it from all directions. You
Yeah,
know?
you have kind of this three-pronged attack meta, if you will. Like you have the warming ocean that's melting sea ice from below or
Mhm.
preventing it sometimes from even growing enough. And then you have the rising air temperatures, right, that are
Mhm.
also going to cause that melting and create like what you had, Tom, there on that cover, those blue meltwater ponds. What that's going to do is absorb more of that heat and then causing more and more melting. And then you have the human impact on top of that, which is what I've been recently looking at. That's the black carbon and the microplastics. Not the microplastics, we know they're everywhere basically at this point. The optical effects, like what it's actually doing, is it reflecting or absorbing heat, is still pretty new research as to what those impacts will be as far as affecting albedo, which is what Tom was talking about, that reflectivity. So yeah, the Arctic and Antarctic are different setups. So you have the ocean versus the land-based ice.
Mhm.
But of course, you also have Greenland in the Arctic, which is land-based ice that's going to be mobilizing and is mobilizing into the ocean, which is causing the sea level rises. But there's been in the news that Antarctica is gaining ice. You've probably seen that. And how do you explain that? And Tom can speak to
Hold
this
on.
too.
This news about what again?
Antarctica, the land-based ice receiving more snowfall in
Oh yeah, that they're surprised that there's been a lot of snow. Why is that? Or is that of real importance?
Yeah, and so it was temporary for a few years in 2021 to 2023. It's and Tom, you can speak to this too, but because of just warming oceans and warming air, you can just hold more moisture in that warmer air, and so more precipitation in a time of climate change is not unexpected. Now, even if the land-based ice is gaining some, the problem in Antarctica is still the sea ice, that frozen ocean is still declining. So let's think about we have a mass of ice called the ice sheet on Antarctica that's all land based. If that ends up in the ocean, sea levels will rise tremendously. Like there's huge potential there. So you have an ice sheet and then you have an ice shelf. That's the part of the sheet that's kind of sticking out into the ocean, kind of hanging out. And then you have the sea ice surrounding it, and that's the frozen ocean. So if you're declining, so even if you're growing land based ice, if you're declining that sea ice, you are then exposing those ice shelves to more of the wave action, for example, because the sea ice is kind of protecting it from that, which
Mhm.
means you can break those ice shelves more easily or allow more heat to get underneath and
Mhm.
melt them. Then what happens? If you break off those ice shelves, that land-based ice ends up getting mobilized. And now you have a lot more ice that might end up in the ocean. So that's how that whole system is connected. And so when you see those headlines about, oh, it's fine, Antarctica is gaining ice, it's like, wait, wait, wait. Let's look at the time frame we're talking about. Let's see what that actually means. It corroborates with what we expect in a time of climate change based on the physics, right? But now we also need to be looking at that whole system and how it's reacting. So
Mhm.
yeah, Tom, I'd love to hear more from you because of your expertise in the sea surface temperatures.
Hold on.
Like,
This is all a wonderful jumble. I mean, we started in Norway, and we're on an ice shelf in Antarctica, and in the meantime, we were talking about magnetic poles. Uh, let's get a little organized here. Let me go back a little bit, and because this magnetic pole thing kind of caught my attention, I gather it's really not that important. But you did mention that there are three poles involved: the real North Pole, the magnetic pole, and then something else. Now, my guess is that this magnetic pole doesn't really have anything to do with the other research that you're doing about climate change. Because if the magnetic pole moving around means anything, it's because of something going in the center of the Earth and not because of anything on the surface. Is that right? Or do you suspect that there is any connection?
No, it was more just like it's an interesting place we visited, but also its location was a great spot where we got off the ship, and why not sample there as well and see and do a comparison. So I ended up doing a comparison between the geographic North Pole, the magnetic North Pole, and then the pole of inaccessibility. What that is, it's the furthest point basically in the Arctic Ocean from any land in any direction. So it's not been reached until last year when the same ship that I was on reached it for the very first time. It's just that challenging because the ice is a lot thicker in that region as well. So, and imagine it's, I can't remember the exact distance now from the geographic North Pole, but it's because it's so far, it just means that the logistics of getting there for anyone who would want to ski it, for example, is very, very challenging, and why it hadn't been done, hadn't been accessed before.
Okay.
So it being the most kind of remote part of the ocean and the sea ice there, I was very curious to see, well, do we still see pollution there? Right. And so do we? Yes, we do. It's not as bad as in like the North Pole is probably the dirtiest, if you will, as far as finding microplastics and black carbon. Just initial visual analysis. We're still processing the results in the lab and looking at the bigger picture story here. But none of the samples were clean. They all had something present in them, whether it was black carbon or these microplastics. So for me, that was very interesting that in the most remote part you can get of the Arctic Ocean, we're still seeing our impact.
Now, what do you suspect these things like macroplastics are going to be doing to the climate, if anything? I know what you think, or at least I think I know what you think about black carbon, but microplastics, that stuff is in our bloodstream and stuff too. I don't know what we have to. 5 years ago, nobody was talking about that,
Right.
and now we're looking at finding it everywhere, and I don't know whether you think there's any impact on the climate.
Yeah, I mean, it is new research for me as well. So I just partnered up with a few institutions just recently to be doing a deeper dive into this. First, trying to identify how much is present, and then trying to actually identify what they are and what maybe is it localized? Is it kind of a more regional transport? So that's the next phase. And then the optical effects, right? What is it actually doing? Is it reflecting solar radiation? Is it absorbing? It depends on the color. Essentially, it depends on the size and the abundance. So that's something I'm going to be looking at in more detail. But the thing is, it's still a question of what, if you go back to ships were polluting not just with black carbon, but with sulfates, right? Sulfates are able to reflect solar radiation.
Yeah.
So in some ways it was helping us cool, but it was also having an impact, right, to our air quality. So once the sulfates were cleaned up, we had a rise in warming, but that's because of the black carbon. So, there's absorbing patterns and reflecting patterns in these particulates in the air. And so with microplastics, it's still active research about what it's going to do for the climate. But for human health, you're absolutely right. It is being found in our bloodstream, in our bodies, passing the blood-brain barrier, right? So and those effects are still also being figured out about, well, are they causing things like dementia, or are they causing heart attacks, heart disease? There have been a few studies that have showed like, well, these people died from heart attacks and we found nanoparticles of plastics, but you can't exactly say, well, that was the cause yet, right? But that's also active research.
Okay, so now you've satisfied my curiosity about poles. which I guess I don't have to worry so much about. I'll focus more on plastics. And of course, black carbon. Now, this trip of yours, was the purpose specifically to collect samples of ice and snow and analyze it for the pollutants, or were you looking for other things? What was the objective?
Yeah, it was mostly looking at primarily my research is in black carbon, and I was interested in its effects on the snow that covers the sea ice because that's going to be the most impacted by solar radiation. But there was a team of scientists that were also drilling cores of ice
Mhm.
to see how thick the sea ice was that we were getting through and testing it for strength because that could tell them about how old the ice was using a combination of variables. So when they would drill out some of these pieces, I would ask for an extra piece of core. And I have measurements from the top and bottom of the core to see about how many microplastics are present and where it's more abundant at the top or bottom. Now, I don't have those results yet, but that was also something that I was interested in, not just the snow, but the ice itself. And then also did some sampling of the water down to about 500 feet depth to look for PFAS. That's shorthand for basically the forever chemicals. And that's the stuff that you find in Teflon, for example. And do we find those chemicals in Arctic waters as well? So those results we're still pending because we just got back at the end of September. Hopefully you'll have something in a few months because I hadn't seen anyone really looking for the presence of those chemicals. Maybe at the surface it's been done, but not with that depth. And so we did a few depth profiles to also see what we'll find in the Arctic. And so that was done at each pole as well. So the geographic, the magnetic, and that pole of inaccessibility to compare.
Mhm. Okay, now I'm curious about so if you go further down or farther down into the ice, I presume that's earlier, that the farther down you go, the earlier it was deposited, right? And would that still contain things like black carbon from uh, forest fires? Right now, I assume that a lot of the carbon that's being deposited in the Arctic or elsewhere would be coming from all these fires that we're having that are caused by global warming. But maybe we're having more fires now than we used to. And were there times when there were lots of natural forest fires in the
Yeah.
past?
Now it's really interesting. And actually, next week, I'm going to a fire and ice symposium in Banff, Canada, where they're going to be talking about exactly this, the ice and the wildfires. Um, from what we looked at in this location in the Arctic, it's first year ice. So I assume at the bottom, when it was just forming, it probably did collect some information from the forest fires from this year, right, from the summer. But the problem is a lot of our evidence is melting away from this first year ice. Where I would like to look for this would be where that thickest multi-year ice is and the 4 to 5 meter kind of thickness along the coast of northern Canada, because Canada's had a lot of wildfires. So actually, I would look for a signal there. So if I could, I'd love to drill a core there and actually see if you can see those wildfire signals.
Why can't you be my guest?
Well,
I'm a Canadian.
yeah,
I invite you to come and share my ice with you.
Yes, write a grant and I'll be right there. I actually am Canadian as well. I have dual
Okay.
citizenship. So yes, I would love to come and do that research. Problem is the access, right? Like it's quite thick ice. You don't really want to be breaking it to go study it.
Yeah.
And so going on foot or on ski as it were would be one way, but then you also have polar bears. So a lot of logistical challenges, but it would be interesting because I think there would be an interesting record for sure in that multi-year sea ice. Now I know there's land-based ice cores taken, for example, from Greenland, where you can see those signals. And it really depends on where you're sampling. You really want to do it now because, again, the evidence is melting away on a yearly basis. So.
Okay. I'm going to be doing a show in a week or two with an old friend who's an expert on forest fires
Wow.
at the University of Toronto. So I'll ask him if can we get a deal for you to come and look at our ice. Okay, so now tell me some more. I have heard now. If you don't mind, I want to go to the other pole. because I have heard that strange things have been going on in terms of temperature and as well as the surprising, or maybe it's not so surprising, addition of a lot of snow in Antarctica. Tell me about what's going on in the South Pole.
I mean, I think your explanation is right. There's warmer water closer to the shore, so therefore there's more evaporation. That's, I mean, for example, the ice ages were triggered when Panama formed and blocked the flow of Atlantic water into the Pacific. It then turned around, formed the Gulf Stream, and dumped warm water up in the North Atlantic, where it caused the snow to fall that built the ice caps in both in North America and Europe. So,
Oh, really? Slow
yeah.
down, because
Oh,
you
yeah,
just said
yeah.
the most
That was
amazing
about
thing.
3.5 million years ago or so. And
Ah,
Panama was an open ocean, and then the volcanoes rose and gradually filled it. And so that changed global ocean circulation. It triggered the ice age. So,
And it's why we have El Nino, right? Like that's why we have
yes,
El Nino because we wouldn't
yes,
have it otherwise without the closing.
yeah, that's right. Now, I'm also Panamanian too. But the thing is that what I've been doing is studying temperature to map out coral bleaching. And in doing so, I've been doing that since the satellites went up with the radiometers back in the early 80s. So I just kind of look at the stuff every day. And what began happening a few years ago is that I'm basically mapping out the high temperature anomalies in the ocean in the tropics. But what I began noticing a few years ago is the biggest anomalies were now no longer in the tropics or mid latitudes. They're appearing in the polar regions, particularly the North Pole, because water gets in there, you know. And the South Pole is protected by this incredible current, the strongest current in the world, really. Um,
is
so,
that the
um,
Humboldt current?
no, not the Humboldt current. This is circumantarctic current.
Oh, okay.
Humboldt current goes up the coast of Chile and Peru and Ecuador.
Mhm.
And that's very important too, for a lot of reasons that we don't really need to get into here. But anyway, I've been mapping the temperature anomalies. In the recent years, I've been getting the most extreme ones have been in the Arctic. Now, I wrote some papers on the temperature anomaly maps of 2023 and 2024, which are both record hot years. Okay, and so in those, I really noted these huge excess temperature anomalies in the Arctic spreading from the Norwegian Sea into the Barents Sea. So it's coming from the Atlantic. So it's essentially heat that is coming from the tropics because most of the heat is absorbed in the tropics. It's being transported by the Gulf Stream. And basically, the Gulf Stream flows into the Norwegian Sea to Spitsbergen or Svalbard, where Ulyana joined the ship, and then it flows into the Russian Arctic, which is called the Barents Sea, and that whole
Oh, wait a
area has
minute.
been
This warm water goes in there and goes into the Barents
into
Sea.
the Arctic Ocean. Yes, it goes over a shallow sill around Spitsbergen, then it gets deeper again, and that has a lot of interesting climatic consequences too that I don't want to get into here. But I mean, the main thing is that we've been seeing these extremely high temperatures in the Arctic in the last couple of years, sometimes 5, 10, 15 degrees C above normal. Okay, that's huge increases. And they've been sitting there for a long time, like more than 20 weeks. So you have 5 months of extreme anomalous temperature in these places. So in looking for that, the thing is that my PhD is actually in atmospheric chemistry from Harvard, and I was the first person to measure methane consumption by forest soils and stuff like that. So the greenhouse gases and measuring them and where they come and go is sort of also my bread and butter besides coral reef temperatures. And so what I was also looking at was the European Space Agency satellite data of what gases they can easily measure from the satellites. They can't measure all of them, but they're concerned. Okay, methane is particularly difficult because methane has a long lifetime in the atmosphere, so it's averaged out over a long time scale. So you need a huge input to be able to see anything because the background is so high. Whereas other gases live for only a very short time. I mean, for instance, the aerosols and black carbon particulates, they settle out in a day or two, a couple days, and they're on the ground again. But methane is going to be 10, 15 years in the atmosphere, so it gets averaged out the whole world. So the short-lived gases are the ones you can see. So I look at carbon monoxide in particular, and nitrogen oxides and sulfur oxides, all those are volcanic sources as well, kind of look at where the sources are. And what I noticed last year with these huge carbon monoxide sources that had the indication that they were coming from combustion of organic matter, and they were occurring in the Arctic Ocean near Novaya Zemlya. And I was baffled. I mean, the only thing I could think that could do that would be a so-called methane bomb. But it's not really showing up in the methane signal, but there's probably a good reason for it. It's just not lasting long enough in one place to show up.
Well, hold on, slow down. I got to absorb a little of this and not much. How would methane yield carbon monoxide?
Well, if it burns, what will happen is it'll be converted to carbon dioxide and carbon monoxide. The carbon monoxide is a measure of the stuff that doesn't completely combust. Okay, and like black carbon too. And there are indications of a lot of combustion, gaseous and particulate products and aerosols and particulate matter less than 2.5 associated with these events. So it does sort of look like a methane bomb, but without a methane signal. So I don't really know what it is. I mean, there are other possibilities. The Russians have been dumping nuclear weapons and explosives into the Arctic Ocean for decades.
That wouldn't contain anything that would explain carbon.
Well, you could have a rusting barrel of radioactive waste blow up, but with methane, here's something that's interesting. I was in touch recently with a Nobel Prize winner in chemistry at Stanford who just published a paper about how something called will of the wisp. It's kind of a glow, an atmospheric glow that you see in pinkish color. And what he's realized is it occurs where methane bubbles are coming up, and the small and the large methane bubbles have different amounts of electrical charge. The small ones, I think, are negatively, and the big ones positively charged, something like that. And where they come close to each other, they actually zap each other with electrostatic charge. And potentially, if you have enough methane coming out with a range of different size, that could trigger an explosion. Now, there's clear evidence of methane explosions in the Arctic Ocean, both on land and in the sea. And Ulyana knows much more about it than I do, but there are, I mean, in the Yamal Peninsula.
Hold on, slow down. Now, an Arctic explosion of that kind would not be something exploding from under the sea, but the gas gets out and then it explodes in the air. Is that what you're saying?
No, it could be from below because gas is escaping from below. But if there's anything that lights it, then you could get an explosion. Okay. Now, I mean, Nadia can talk about the geological evidence for this soon. I mean, that would be very interesting. But for sure, we know there's a lot of methane down there. We know it burns very easily. Now, so I've been looking for explosive events in the Arctic. I hadn't seen any this year, by the way. This was last year that I saw it. It was in August, and it occurred in the ocean areas. It was not associated with forest fires because I can map those out and I can see what their gaseous signals were. Had nothing to do with forest fires. I haven't seen any this year. I have seen unexplained pollution events, both in Russian and Alaskan oil facilities where I think they just burned off a huge amount of methane, or there was a catastrophic explosion that was concealed. Other possibilities are military, explosions too. I mean, and the fact is, it's pretty clear that the Russians are using nuclear power for massive excavation inside the Arctic Circle. And you can see it. You can see it from the gas. I mean, the thing is that when you use nuclear power, you generate a nitrous oxide signal because the high temperature causes nitrogen oxygen in the air to combine to make nitric oxide. It's not a combustion product. It's a product of the high temperature and pressure condition. And I see those signals in places there that I think there's massive underground nuclear explosions for excavation for whatever reason, or something like that. Who knows? I mean, I couldn't guess. So I do look for those, and I did see a huge explosion in Alaska, at Dead Horse, Alaska, where the Prudhoe Bay facilities. But those, you see, these only last a day or two. They suddenly flare up. They're the most intense sources of carbon monoxide in the Earth for a couple of days, and then they disappear completely. The forest fires have a very different signal, and I've been following those in Canada and Siberia as well the last couple of years. This year was not so bad. We're lucky. in that sense. Okay, we're lucky in that sense. But but the thing is, the fact is, the excess temperatures in the Arctic nearly reached levels of 2023 and 2024. So
This year.
there's a potential of methane bombs. Anyway, I'd like to hear what Ulyana thinks about it, because
let me just focus now. I want to know that all of this investigation you're doing about methane and stuff and other nitrous oxide and all that, this is an effort to explain the anomalous temperature rise in the Arctic. Is that the main question?
No, I don't think it explains it. I think it's a result of it, not the cause.
Result of it.
Yeah.
Result.
Yeah, so like in the Arctic, for example, you have these warming temperatures because of that, the feedback between the ice and the ocean, right? You're supposed to have this cap, if you will, of sea ice that's reflecting solar radiation, but because you have so much open water, you're heating the ocean. So now you're starting to heat the permafrost. There's actually permafrost, a permanently frozen ground in the ocean, like the continental shelves, plus on land. And so what Tom is saying, I believe, is that because of that warming, that's what can start to mobilize that methane, because that's trapped in the permafrost, and now the permafrost melting because the temperatures are so much higher. And so, yeah, the important part of this is methane is a more potent greenhouse gas, meaning it can trap more heat. And so if you start putting a lot more of it in the atmosphere, it's worse than carbon dioxide, right? Right now it measures in the parts per billion versus parts per million in the atmosphere. But if you start to put a lot of it in, that is going to be quite damaging to the climate. So that's why it's, yep.
When people talk about methane problems, the first thing they talk about is this methane escaping from factories that are just sloppy in their procedures and don't take care of things. And my impression was that the vast majority of the excess methane, or everything's excess, I guess, because you don't want any of it up there, I guess, but that the problem is caused more by industrial effluents than by these geological changes. Am I wrong, or are they misinforming me? Because I think this is based on real statements that I've read.
There are many sources. The major sources, are basically leakage of fossil fuels from gas lines, and then the fact is most fossil fuel refiners burn their excess methane. They just burn them in huge flares and so forth. So the Middle East has huge methane sources. They're burning like mad all up and down the Persian Gulf, Alaska, some of the other places too. So those are industrial sources. The natural sources are probably the major source, and those are made by bacteria that live in anoxic muds, anoxic environments. In fact, the methane is their waste product. They're breaking down organic carbon where there's no oxygen, and they release methane. On the other hand, there's a whole other group of bacteria that eat methane. Okay, and they rely on the first ones to give them food. Okay, and those are the ones that I studied, because I found that there were a lot of them in forest soils, and that was a natural sink of methane. The other sink is in the atmosphere by photolysis, by ultraviolet light. Once you get above the ozone layer in height, 10, 20 kilometers up, the ultraviolet light breaks down methane. Okay, so it gets consumed completely in the upper atmosphere, but a fair bit is consumed on the ground. For example, when the Gulf of Mexico oil spill happened, there was huge amounts of oil released. Some went up, floated to the surface, some sank to the bottom, and then bubbles of methane all through the water column. And the oceanographers were thrilled, because they thought they would use the methane to track the movement of the water to see where it went. And by the time they could get there to measure methane in the Gulf of Mexico, it was entirely gone. Oh. They couldn't find any. Okay, the bacteria had eaten every bit of it. And so the fact is, and soils and waters have bacteria that they're starving for methane. They're very slow growing. Sort of very odd bacteria. They're very slow metabolism.
Really,
but anyway, there's a natural sink of methane, but it takes a while to operate. So if you have a huge explosive event, then you could get a peak, and then it would come down, whether you would be able to measure in ice cores is problematic because those average out longer periods of time. But anyway, there's clear evidence.
Don't go away, because I really want to pursue this thing about methanotropic bacteria, because I did a talk show about 4 or 5 years ago with a woman who was doing research on the bacteria that eats methane, and in a lab, and she was having a hell of a time because you can't keep the stuff alive long enough to study it. So her research was quite difficult, but much more recently, I read something about how, well, we could just produce massive amounts of these little guys and put them where we want them, and that'll handle our problem. They'll eat up all the methane, and Bob's your uncle. That sort of attitude was expressed in this more recent paper. And in between, I heard nothing whatever about bacteria that eat methane.
Well, they consume about 10% or so of the methane sources. So they're on the average in the world, roughly that. So, I mean, most of it is broken down in the upper atmosphere.
I see. Okay. So that's not going to be our salvation. The idea of making some excellent little germs that are going to eat.
Given enough time, they can do the job. That's the issue. But at any rate, an explosive event, could impact temperature until the bacteria get to eat the methane. And as I say, they're slow growing, so they can't.
And bacteria can be used to eat microplastics, at least, Meta. I mean, like that's research.
I did want to come back to that because let me just say this. I mean, sorry, but before Ulyana talks about explosions, but the thing is that, you see, one thing about black carbon is carbon's been burned to very high temperature. So it's very uniform in composition. It depends on what you make it from, but temperature is what controls its composition. And so worldwide, you heat stuff up to enough temperature, you'll get pretty similar sort of black carbon, and it lasts forever. Lasts millions of years. You can find 350 million year old black carbon from forest fires. I mean, it's forever. The stuff that is not as high temperature breaks down more quickly. So that's distributed everywhere. Plastics is much more difficult because plastics, there's basically a chain of carbon in a plastic, and then all the structural axis with, and then all these side groups that can be any kind of organic chemical with any kind of organic property, any kind of color, any kind of physical properties. And so the thing about microplastics is there's so many that they basically cover the entire spectrum of physical, chemical, and biological properties. Wow. And so people are lumping them all together. They say, oh, we have so many grams of microplastics. Well, they're not all the same. Some of them will kill you dead. And some of them, you can eat all you want and it won't.
Now like the microplastics are even breaking down into nanoplastics. And so that recent paper from Mount Everest is saying the microplastics are probably local, like coming from like what's happening from climbing and from villages, like local. But nanoplastics, because they're so much smaller, can actually be airborne. So that could be coming from a long distance, like even from places in India, for example, reaching the top of Mount Everest. So I find that really interesting. And again, the research is going to be very important to see like what are the impacts on human health as well as planetary health.
Yeah, they cover the entire range of pathogenic behavior. Yeah. By the way, let me mention the PFOS thing that you mentioned. Let me know what happened. My daughter was a regulator of PFOS until Trump fired the people who were trying to do that. So, okay, and so we're very interested in the PFOS.
Sure.
That's every place in the world. Right. Now, and the thing is, it isn't everything. It has all sorts of biological effects that we're barely beginning to grasp.
Hold on. Back up. That term you use, PFOS or something, you're talking about what are they called? Forever plastics?
Forever chemicals.
Yeah. Forever chemicals. Yeah. Okay. Now, but these, how does something become a nanoplastic? It starts, you talk about Lego. I mean, okay, let's something like Lego or my hairbrush or something. That is regular plastic. Then it turns into microplastics, which you're going to find on the North Pole, and then nanoplastics, which they're going to find at the top of Mount Everest. Well, what makes nanoplastics? Is there a procedure or some chemical thing that's going on that produces these things, or is it that every time you have plastic, you're going to have some nanoplastics?
Yeah, I mean, essentially, it's just a size. Yeah, it's basically like when you have something made of plastic, I don't know, like here in my pen, right? And then it can sometimes shed, right? These small little particles. And, you know, you'll see that even from like when you do your laundry, right? If you pull out that lint, it's some of that is just these plasticky threads. So imagine it's not catching everything, your dryer, and that ends up somehow in the water stream. Then through a process of just being in the environment and being exposed to UV radiation, you can actually start to break it down to even smaller particles because of just environmental exposure. So that's really, it's just a size. Yeah. Yeah, well, go ahead.
Maybe, tell me this. So, everything could be nano, right? I mean, this glass, this, everything, not the metal.
Well, black carbon is nano. It's nanograms. Yeah.
Okay.
So, remember this, Meta. The smaller it is, the higher the surface area it has, and the more chemically reactive it has. So there are things that in big amounts don't affect you very much, but you take in the same amount of stuff in small sizes, it reacts very quickly in your body, whatever it does. And I mean, we have every kind of chemical subgroup in these different plastics. So they have the entire suite of possible behaviors biologically.
Yeah, I think remembering correctly, just the PFAS is like over 10,000 compounds, right, of human-made chemicals. So yeah, there's a huge spectrum we're talking about, and that's why it's interesting. What are we finding?
My daughter's identified hundreds of products that are being used that contain PFAS that are not being identified. These are being listed as inert ingredients, and they don't have to say what they are.
Well, look, I mean, there's paint on my wall. There's wood here at the table. Everything around me, presumably, is rubbing off and shedding little aerosols all the time. Are you looking for wood particles in the Arctic? Are you looking for paint particles? What else besides nanoparticles of plastics are you worried about? Is there any reason to worry about, glass or metal or anything else that might be floating around in the atmosphere?
Yeah, I mean, it basically comes down to like the reason there's such interest in any of these, let's call them light absorbing particles or LAPs, is what it can do to the sea ice, right? So that's one part, like that it's just going to accelerate melting if enough of this accumulates. And we can do something about this by trying to reduce the amount of plastic use, for example, or changing fuel sources so we're not generating as much black carbon. So these are actual tangibles we can do if we have evidence saying, hey, this is actually affecting us in this really like sensitive region. It's harder to get like CO2 emissions under control or methane, right? But at least something we can do for our contribution of pollution, right? So that's kind of that big picture messaging. Is it there? If so, how much? And this is something we can solve and scale up, and it's better for planetary health and human health, right, ultimately. Now, yes, we're looking for basically anything and everything in the snow and ice and trying to understand the impacts as well, because, with glass particles, I was reading a recent paper that was talking about how do you actually make the Arctic Ocean brighter. And it was talking about even using these kinds of like microbeads or glass beads and try to stimulate that kind of albedo effect.
This woman at Stanford is very enthusiastic. Actually, she wants to be on a show talking about that. And
look forward to that.
I think that's serious enough to investigate or not. But
I think so, because there's a recent paper that actually investigates like what you need to do just from a computer model perspective. What impacts brightening the ocean, meaning changing that albedo to be brighter, would have, and it would make a significant impact to reducing the amount of heating. But then we get into the geoengineering aspects of it. How do we actually refreeze the Arctic? Can we even do that? So that's where like these glass beads and creating foam, anything that will increase the reflectivity is being researched. So yeah, I think you should talk, Turk. I'd be very curious to actually see like can this actually be done? Is it scalable to what we need? Or is it going to be a short-lived solution? And once the solution goes away or doesn't work, is it going to actually make it worse long-term? Or is it going to pollute more? Right? So there are, I would love to hear actually what you have to say about
I
that.
don't want any glass bubbles in my bloodstream. But I've heard that there's also interest in rice husks, which are like they float on water. You could put them there and they reflect light because they just, float around.
But rice and methane, not a good combination though. So
no,
rice cultivation can generate a lot of methane too. So again, we're trading problems here.
Rice paddies are a major global source.
Yeah.
And termites are too.
These people eat white rice all over Asia, so they polish the rice, and this rice, husk is going to be there, whether or not you burn it or bury it or sprinkle it in the ocean. And I don't think you're talking about raising rice just for the sake.
I wouldn't do that. Like growing more for those purposes, no. But if it's already there, well.
Yeah, no, actually, this guy has a different idea. He's not trying to grow rice. He's trying to use rice husks to dump in the water.
That's already present,
Trying to dip them in metals and trying to stimulate phytoplankton blooms and then sell carbon credits. So that's a lot. But coming back to your question about fine particles, Matt, I mean, operationally, what they do is they measure with filters, and 2.5 microns is sort of the standard for the fine stuff. So PM 2.5 is stuff smaller than 2.5 microns. And people worry about that because that gets absorbed in the lungs. So, you don't want to breathe that stuff in. But if you look at the PM 2.5, it has a lot of different sources. For instance, in the Sahara Desert, it's mostly wind-blown dust. Over the oceans, it's almost entirely salt spray that is evaporated. Okay, over land, it's a mixture of fossil fuel combustion and forest fires. And so all of these things, vary tremendously in amounts, but they produce these fine particles. At 2.5, I don't know, Ulyana, where's the boundary for nanoparticles?
I'm not sure offhand.
I think it's even smaller than
It's even smaller, yeah. But yeah, you raise an interesting point with the PM 2.5. So right, like if you have a sensor out in the ocean and you're measuring high amounts of PM 2.5, is that pollution from ships or is that, the sea salt spray?
Mostly that's salt spray.
Right. And so that's why it's important to look at what's happening in the air as well as looking at what's on the surface of that snow or that sea ice. Because if you're getting a spike in PM 2.5 in the air, maybe it's just the sea salt. But if you're also seeing a spike in the sea ice, okay, maybe there's a correlation there of pollution. So you see, you need multiple pieces of evidence. And that's why I think you still need to be physically sampling these places and looking for it visually.
I just love the fact that I bring these you two guys together, or sometimes other pairs of scientists together who can talk to each other in this arcane language that I have no idea what you're saying, but I'm having fun just knowing that you are actually exchanging ideas that might be useful to each other.
It stimulates new ideas sometimes where you think science, there's a lot of collaboration that can happen and there's a lot of interdisciplinary work that can be done, right? Like you're saying, we're talking about tropics and polar regions and they are connected to what's happening, because we're talking about a whole global system. Why are we having these kinds of releases in the Arctic? It just makes total sense of just permafrost, right? So again, it's supposed to be permanently frozen ground. And literally the ground, like in Siberia, for example, and then in the actual continental shelf regions, they're called these methane ice clathrates, these structures where that methane's bound up with the ice. And so when you're getting increasing ocean temperatures, you can start to mobilize that methane if you start to melt those clathrates. And then in Alaska, for example, you also mentioned Alaska, you can visibly see these impacts. You can see the infrastructure tilting, right? Was that permafrost is melting. I mean, there's just actual visual evidence of pieces of this land falling into the ocean. One of my colleagues set up a time-lapse camera that actually could see coastal erosion of this permafrost melting and breaking off and then going into the sea. So yeah, we are talking about a lot of methane stored up for millions of years. In some cases, it's a slow release, slow melt, but then there's a buildup that can happen. And they're localized right now, and they're The problem is if you have the chain reaction, right? If you start this whole process of melting like all of Siberia's permafrost, then you're really like setting up for a situation. And I don't think, Tom, correct me if I'm wrong, that the models are really accounting for how quickly that can unzipper, if you will, like this chain reaction of events once you start that process. Right now, it's mostly kind of localized in some places with, large explosions, but it's not quite chain reacted yet. But yeah, I'd love to hear if you know anything else about it, but that's the extent.
Let Tom answer you.
No.
Tom's got to come back another day.
Okay. A whole conversation on just that.
We're all over time, and
right.
I can't edit this out. It's just too good. It's and
to be continued then.
Yeah, it's great fun. I've enjoyed it very much, and I want you to come back and talk to me some more because it's very important and very, very interesting. Okay?
Yes.
All
Sounds
right.
great.
Take care. Bye.
Thank you.